Thank you everyone for joining us for this webinar. I'm sure you have learned quite a lot from previous experts. My name is Bing-jie. As I mentioned, I'm currently working at the University of New South Wales, and I mostly work on wastewater treatment, especially biological treatment and greenhouse gas emission mitigation, and also bioenergy or liquid phase energy recovery from wastewater and sludge. So in this presentation, I will present or introduce briefly of my recent work about transforming sewage sludge into high-value liquid bioenergy. So as we all know, our society and every one of us are currently using natural gas, natural resources to supply the energy demand. However, this kind of energy or natural resources are finite, right? They are limited. They may consume up in next few decades. So we need alternative or for this kind of natural resources. So we call this kind of alternative is normally renewable energy resources. This is quite urgent, right? Because if you look at the energy consumption, we currently consume majority of the energy from natural sources like natural gas, oil, coal. But however, we only have a very little percentage, like around 7% of renewable energy supply currently. So we need to find more renewable energy resources, right? In the meantime, wastewater treatment plants, as we all know, they produce a high quantity of sewage sludge, and the amount is increasing because we have more wastewater treatment plant is developed or built in different countries around the world, right? So we have a lot of sludge disposal, which actually account up to sort of 60% of the total operating cost of wastewater treatment plant, which is high cost burden, right? So currently we actually using those sludge in some countries, some wastewater treatment plant use a sort of a recovery strategy to produce gaseous energy, that is methane, right? Biogas, not pure methane, the biogas. However, this kind of method actually are dealing with a gas phase energy, which are not so convenient for collection or storage, transportation, right? And this methane, carbon dioxide in the biogas may leaking as a greenhouse gas. A lot of them may leak due to not well handling during the operation. So a lot of greenhouse gas emission from anaerobic digestion in wastewater treatment plant. Based on this kind of background, we propose trying to propose a new sort of a pathway to convert sewage sludge into liquid phase energy, that is liquid bioenergy, for example, right? If we can do this, it's actually a win-win strategy because in one side, we reduce the greenhouse gas emission, that is methane and carbon dioxide. In the other side, we produce a sort of a easy collect or storage liquid phase bioenergy. Especially, we can use a chain elongation process to produce middle chain fatty acids, which are very high value, sort of high value chemicals, may give us more intensive energy generation and to reduce greenhouse gas emission from conventional anaerobic digestion, right? So what is middle chain fatty acids? Basically, this is a kind of fatty acids containing 6 carbon to 12 carbon with one carboxylic sort of group in the fatty acids. This kind of middle chain fatty acids have high energy density because they have a higher carbon to oxygen ratio, and also they have a longer carbon chain to allow them easier separation from water, right? And because it's a liquid phase energy, it can be easier to collect, storage, and transportation. And also, these middle chain fatty acids have a wide applications. For example, in industry application, can use it as a renewable diesel, and also can be used as the animal feed for livestock farming, and also it can be used for medical and food processing process, all right, as a food additives, for example. So based on this kind of background, we propose to use sewage sludge as a feedstock to produce mid-chain fatty acids. So we convert to produce liquid phase bioenergy. All right. Our first step is to develop a two-stage system because we need electron donor and electron acceptor to do the chain elongation process to add more carbon to sort of short chain fatty acids and then produce middle chain fatty acids, right? So in this kind of process, we use two stages. One, at the first stage, we just convert sludge to produce short chain fatty acids, which is easy and well established, right? So we can use sludge fermentation to produce short chain fatty acids like acetate, propionate, or butyrate, right? As an electron acceptor. That's the first stage. And then we use another stage as a second stage to do the chain elongation process. We just add some sort of electron donor into the system, into the short chain fatty acid system, which normally is ethanol as an electron donor, right? So we upgrade short chain fatty acids to produce middle chain fatty acids using ethanol as an electron donor, right? To test such two-stage system, we actually design a few different ratio of electron donor and electron acceptor. And then we test the three different categories, and these results actually showing that MCFA production increase with the increase of the ratio of electron donor to electron acceptor, right? And then the highest middle-chain fatty acids selectivity was achieved as sort of at the ratio of 1 to 1. That is the sort of optimal ratio of electron donor to electron acceptor to produce middle-chain fatty acids from short-chain fatty acids, right? And then we look at the metabolic pathways to do metabolic pathway analysis of this two-stage system, trying to understand how this chain elongation process was occurred. So we did metabolic pathway analysis through metagenomics, all right? And then we can look at these results. We identify two different pathways here. One is the FAB pathway, which is fatty acids biosynthesized pathway, and another one is reserve beta oxidation pathway, that is RBO pathway, all right? So two pathway was identified in this system. And then we also look at the key species who regulating the process, and we found a few key genus and key species was enriched in the two-stage system, which actually involved in both RBO and FAB pathways and has a positive relationship with the ethanol levels. Basically, so ethanol actually play a critical role here to promote the chain elongation process to produce middle-chain fatty acids. And then we understand how these two-stage systems work, and then we're trying to combine them into one-stage system, all right? So we're trying to simultaneously produce short-chain fatty acids, but also insidely use them, consume them to produce middle-chain fatty acids in suit, all right? So in one-stage system, basically we put sludge in one reactor and then adding the electron donor, which is the ethanol in this case, and put them together, trying to produce middle-chain fatty acids, all right? So you can look at the result here with different ethanol levels, we produce different level of middle-chain fatty acids, right? And we also found the increasing level of ethanol resulting increasing MCFA production. And also, interestingly, we found the sludge, the was is waste active sludge, the sludge degradation was also improved by the ethanol levels, right? So basically, we successfully combined two stages into one stage and to achieve middle-chain fatty acids from sludge. We also look at the microbial community structure of this one-stage system, and we can say the clear shifts of microcommunity was observed with the involvement of ethanol, right? So which also confirmed the critical role of the electron donor. And then we found the hydrolysis, acidification, and the CE process chain elongation microbeads were all enriched in the reactor in this one-stage system with mini-chain fatty acids production, right? So these key steps here were all enriched by the system. So we can see the ethanol as an electron donor play a critical role in this one-stage system. And then afterwards, we start look at the key factors on the performance and the metabolic pathways of this one-stage system, all right? So the first key factor we think about is electron donor. As I just mentioned, electron donor, the ethanol we tested previously play a very critical role here. However, if you look at the literature, we found that there is quite a few electron donor you can use to do the chain elongation process, right? So not only ethanol, but also, for example, the lactate and the combination of those two with different ratio, all can play as a role to produce, to do the CE process, chain elongation process, and then produce mini-chain fatty acids. Okay, so based on this background, we then using the one-stage system we develop, and then we test 5 different conditions of electron donors. So we use different electron donor conditions. One is ethanol only, and then lactate only, and then we do combinations of those 2 electron donors with different ratios. Here, showing here in these figures. And then we can find based on all these results, we found ethanol actually as the sole electron donor was still the optimal strategy to produce highest production of mini-chain fatty acids. All right, and the selectivity of the mini-chain fatty acids from sludge is still the highest one by ethanol dosing. Okay, and then if you look at the lactate group, and you can see lactate actually result in the lowest mini-chain fatty acids production. You can see from these figures, the red column is for the mini-chain fatty acids groups, and you can see lactate produce the lowest concentration, right? And for the other combination groups with different ratio of ethanol and lactate, we found they produce relatively higher mini-chain fatty acids than lactate group, but lower than the ethanol group. Right, and we have found a different composition of the outcome of the effluent from the reactors. You can see ethanol as an electron donor actually produce more carburet, but with co-donor, which will produce inethanate generation from the group. All right, so different combination. And then if you look at this single group of those components like short chain fatty acids and mini-chain fatty acids and alcohol, you can see still the similar trends, like the ethanol produce the best results among these tests, right? Okay, and then we look at the metabolic pathways with those different electron donors. We actually constructed the 5 group of the results for the metabolic pathways like CE with ethanol, with lactate, with combination of them. You can see different color lines indicate different groups. And then the 2 metabolic pathways like the RBO and FAB, both was enriched, but with different extent, right? You can see the functional genes in connection with mini-chain fatty acids production were all expressed. However, the highest level of gene expression actually related to the CE cycle observed in the ethanol group. Okay, so ethanol actually play as the best or optimal electron donor in these conditions. And then we found that there is no significant synergistic effect of co-electron donor system, right? So this might be due to the competitive acrylate pathway showing here, right? Because this pathway also use or produce carbon-3, for example, which may compete with those CE process, which also use short-chain fatty acids. And then the second key factor we look at is pH, because we know pH always play an important role in anaerobic fermentation process. We test 3 different pH value, 5, 7, and 10. We use long-term experiments like a few months, for example, and then to monitoring the production performance of medium-chain fatty acids. And then we also look at the metabolic pathway here, similarly with previous slides, and we look at the 2 pathways, and then we found the pH 10 actually almost no medium-chain fatty acids production was found in the group, and then the pH 7 and pH 5 both produce quite suitable for medium-chain fatty acids production, right? In terms of yield, selectivity, and composition, mainly was carburet with longer chain, right? And then if you look at the metabolic pathways, we found CE related genera were enriched both at pH 5 and pH 7, and with very specific species was identified as a main contributor. Especially, we found a new CE sort of functional genes, right? Functional bacteria was only found at pH 7, and then the highest expression level of gene related to hydrolysis, short-chain fatty acids production were only observed sort of at pH 10, right? Alkaline pH conditions, because there is no medium-chain fatty acids production. We only have a short-chain fatty acids production in this condition. And then we look at the temperature, the effect of temperature. Again, we use a long-term experiment to test different temperature. Here we test the 3 different group of temperature, 25 degree, 35 degree, and 55 degree. And you can see from this figure, again, the 55 degree actually is not suitable for medium-chain fatty acid production because almost no production observed. And then we found the CE process was successfully performed at both 25 degree and 35 degree conditions, especially 35 degree conditions is more efficient for medium-chain fatty acids production, especially in terms of years and the stabilization time. You can see from these figures, right? So the blue line actually the medium-chain fatty acids concentration here showing. So more or less, the 35 degree is more suitable for the one-stage system. And then the last factor we are looking at is a solid retention type, the SRT, right? We use a similar approach to running long-term continuous experiments, and we test 3 different SRT, which is 7 days, 12 days, and 15 days. And we found, if you look at the blue line here, which is carboxylate, and they are more or less on similar level, right? So on the appropriate pH value, which is 7 applied in these groups, and the temperature of 35 degrees, we found the effect of SRT on the performance was not significantly different, right? And then based on this, we thought the shorter SRT might be increase sludge loading rate and decrease the reactor size. So we may reducing the operation cost if we use shorter SRT rather than longer SRT in one-stage system to produce medium-chain fatty acids. And then afterwards, once we understand how the key factors are effect of the system, we now trying to enhance the production performance by using pretreatment technology or pretreatment approach. All right, because we know sludge system is hardly degradable. There is a lot of particulate substances are not easily degradable. So we can use pretreatment approach to help enhancing the production of medium-chain fatty acids to sort of converting more organic carbons from sludge to mid-chain fatty acids. The first strategy we use is FA pretreatment. So we know FA is recoverable chemicals which can be obtained directly from the anaerobic digester liquor, right, from the waste stream plant. So easily accessible, which is can be used directly for the pretreatment. The technology actually, if you look at this figure, the FE you can obtain from the thickener, and then to do the pretreatment. After pretreatment of the sludge can go through the fermentation process to produce sort of mid-chain fatty acids, and then the FA. The remaining FA can go through the FA production process again, and then to produce FA for the pretreatment. In this way, we form a circular pathway for the whole sort of sludge resource recovery process. Now we test different FA levels for the pretreatment. We found that the pretreatment actually enhanced the production performance with different level, and then the FA concentration of a certain level, for example, 255 milligram per liter, actually the best pretreatment strategy in this condition, right? And also the pretreatment shorten the lag phase of mid-chain fatty acids production process, and then during the pretreatment stage, the sludge actually sort of have a smaller product size, and then the lower hydrophobicity, right, to improving its disintegration. And then during the fermentation stage, the pretreatment actually enhance the hydrolysis, acidification, and the CE process, all of them, right, relevant to mid-chain fatty acids production. And then the second strategy we used to improve the performance is we dosing, not pretreatment, but dosing ZVI directly into the fermentation system. If you look at this system, we found that we use the experiment to test different performance on a different level of ZVI, and then we found the ZVI actually declined the ORP, and then to creating a sort of more favorable environment for the fermentation process. And then the ZVI also have a strong conductivity, which can act as an electron shuttle to contribute to increasing electron transfer efficiency, right, for electron donor to acceptor, which can produce more mid-chain fatty acids from the system, right? So the key fundamental understanding of this is a lower ORP, but with higher conductivity, and also which can sort of act as a pH buffer here to provide a better environment for microorganisms enrichment in the system, right? And then the last strategy we used is similar like ZVI. We use biochar, right? Biochar, which can actually produce directly from sludge, right? Hydrothermal process of the sludge to produce a hydrochar. And then we use two different hydrochar, which is coarse biochar and fine biochar, right here. So fine biochar has smaller size, and coarse biochar has a bigger size here, right? So we use two different sizes, and then we found both biochar can produce more mid-chain fatty acids than without biochar addition, right? Those biochar has similarly has a redox properties with the important ability to charge and or discharge to promote the electron transfer efficiency, similar like as ZVI, right? And then the abundance of functional enzymes associated with CE cycle. Here you can see the RBO and FAB are both sort of increased by the biochar mediated, right? So biochar actually also can improve the performance of the one-stage system. And then all these kind of previous slides actually we introduced are using ethanol as an electron donor. This kind of approach, we highly depended on the electron external addition of electron donor, that is ethanol. But ethanol actually are kind of resources we can't sort of consume up of ethanol, right? We better use renewable sources to produce ethanol rather than to purchase ethanol from market, right? So if we can use the system to generate ethanol by themselves rather than to externally donor, right? So we can use this kind of in-situ electron donor as a to produce mini-chain fatty acids react with the electron acceptor. In this way, which we can propose a novel sort of a fermentation paradigm, right? So in this way, we can remove the key barrier to replacing the external electron donor by self-produced electron donor in the system, right? So in this way, we don't have to add any electron donor anymore, but we can produce in the system, within the system. So what we can do here is we provide a dry yeast, which is very cheap and readily available, right, into the system, using this yeast to produce ethanol in situ, and then to consume these produced ethanol as an electron donor, and then to work with the electron acceptor, that is a short chain fatty acids, right? And then to do the chain elongation process to produce mid chain fatty acids. Okay, so we first using batch test to test this concept. You can see the control and experimental system. The experimental system, we use dry yeast as an incarnation in the system, and then the control without dry yeast, right? You can see the clear difference here. In the control, we produce nothing here, without any ethanol, without any mid-chain fatty acids. But for the experimental group, we produce a high level of ethanol at the initial stage, and then we use them up to produce mid-chain fatty acids, right? So you can see the dry yeast inoculation actually achieved in-situ production of ethanol from sludge, and then this ethanol produced can be used as an electron donor to produce mid-chain fatty acids by consuming those donor and the short-chain fatty acids. All right. So also we found some long-chain alcohols was also produced in this system, and we can confirm through this batch test introducing yeast into the system can improve the mid-chain fatty acids production and also the COD dissolution of sludge. Okay. And then afterwards, we test the long-term experiment setup. We're using a few months. We tested a few months using continuously feeding system. We found in the continuous system, again, the yield of mid-chain fatty acids and long-chain alcohol both successfully sort of produced and reach a stable level after a few months operation. And then the composition of the mid-chain fatty acids was quite consistent with the batch results. And then with ethanol and acetate, propionate was produced at the initial phase. If you look at the COD balance flow here, you can see the ethanol, acetate, and propionate were produced first, and then those will do the chain elongation process to produce carborate, valerate, and then the longer chain sort of fatty acids. All right. So this long-term continuous experiment also confirm the strategy of using dry yeast to produce ethanol in situ, and then to as an electron donor to produce mid-chain fatty acids. And then with this system, the long-term system, we look at the metabolic network map. If you look at here, we test the gene expression and gene abundance. We found the excellent transcriptional activity of key enzyme genes with yeast involvement, all right? And then this species introduced by dry yeast was maintained in the system with a very good transcriptional activity. And then the potential pathways regarding the, for example, the short chain fatty acids production and ethanol fermentation and chain elongation and LCA pathways all constructed here, which confirm the successful of the strategy using dry yeast to produce ethanol in suit. All right. And then lastly, with this new paradigm, we trying to using life cycle analysis to confirm and to assess the environmental impact of this new system, right? We look at the chemical using and the land using, toxicity, electricity using, and all the consumptions, all right? And outcome, for example, the mid-chain fatty acids, short-chain fatty acids, and then we use a life cycle assessment and confirmed the overall sustainability of this new strategy, right? Using dry yeast environment, right? This mainly sort of eliminate the environmental burden of industry ethanol production process, because we use in-suit production of ethanol rather than using external ethanol addition, right? That's one key aspect of this new strategy. And then another point is the solid waste disposal and extraction solvent addition were important contributor to the environmental impact based on the assessment. And these results actually provide a sort of insights into the strategy for future application into different waste, bio-waste, rather than only sewage sludge, right? We can use the biomass, different biomass like the food waste or even microalgae as a feedstock to produce mid-chain fatty acids based on this strategy, right? So with this, I just finished my presentation for transforming sludge into mid-chain fatty acids. Okay, so